In a striking demonstration of how far nanotechnology has progressed, researchers have engineered a QR code so small that it exists below the scale of most living bacteria. Measuring just under 2 square micrometers, this structure is invisible to conventional optical microscopes and can only be resolved using electron imaging techniques. While this achievement has earned global recognition for its size alone, its true significance lies not in miniaturization, but in what it reveals about the future of long-term data storage. If you like my videos, subscribe my channel and press the bell icon to turn notifications on so you keep getting all the major advancements in science and technology. And don't forget to like and share this video with your friends and colleagues. At its core, the work addresses a fundamental weakness in modern information systems: impermanence. Today's dominant storage technologies, magnetic drives, solid-state devices, and cloud infrastructure, are inherently fragile. They depend on continuous power, controlled environments, and periodic maintenance to preserve data integrity. Even under ideal conditions, degradation is inevitable. By contrast, this new approach encodes information directly into the physical structure of highly stable ceramic materials, effectively transforming data into a form that can persist without energy input for centuries or potentially far longer. The technical challenge is not simply writing information at such small scales, but ensuring that it remains both stable and readable over time. At the nanoscale, materials behave differently. Atoms can migrate, defects can evolve, and tiny structural changes can erase stored information. To overcome this, the researchers utilized advanced thin-film ceramics, materials originally developed for extreme industrial environments where resistance to heat, wear, and chemical degradation is critical. Using focused ion beam techniques, they etched the QR code into this material with nanometer precision, creating pixels far smaller than the wavelength of visible light. This ensures both structural durability and resistance to environmental decay. What makes this approach particularly compelling is its scalability in terms of information density. Because the encoding occurs throughout the material at extremely fine resolution, the potential storage capacity is immense. In principle, vast amounts of data, on the order of terabytes, could be embedded within a surface no larger than a standard sheet of paper. More importantly, unlike digital storage systems that require continuous energy to maintain bit states, this method is entirely passive. Once written, the data remains physically embedded, eliminating the need for power, cooling, or active error correction. From a broader perspective, this development reflects a shift back towards a much older paradigm of information preservation. Ancient civilizations recorded knowledge in stone, clay, or metal, media that have survived for thousands of years. Modern technology, despite its sophistication, has largely sacrificed durability for speed and convenience. This ceramic-based approach effectively merges these two philosophies, combining the permanence of physical inscription with the density and precision of modern nanofabrication. There are also significant environmental implications. Data centers currently consume vast amounts of electricity, not only for computation, but for maintaining stored information. As global data generation accelerates, driven by artificial intelligence, high-resolution media, and scientific research, the energy cost of storage is becoming a critical issue. A storage medium that requires no ongoing power could dramatically reduce this burden, offering a more sustainable alternative for long-term archival data. Of course, the technology remains in an early stage. Writing data at such high resolution is currently slow and requires specialized equipment, and reading it back depends on electron microscopy, which is not yet practical for everyday use. However, these limitations are primarily engineering challenges rather than fundamental barriers. With further development, faster fabrication methods and more accessible readout techniques could make this approach viable for real-world applications. Looking ahead, the implications extend beyond simple QR codes. The same principles could be used to encode far more complex data structures, including full digital archives, scientific datasets, or even cultural records intended to outlast current technological civilizations. In this sense, the work is less about creating the smallest QR code and more about redefining how humanity preserves its knowledge. Ultimately, this breakthrough suggests a future where data is no longer something that must be constantly powered and maintained, but something that can be physically embedded into matter itself, stable, silent, and enduring across